My name is David Kipping. I'm a professor of astronomy at Columbia University and director of the Cool Worlds Lab.
The Search for Habitable Worlds and Extraterrestrial Life with David Kipping. Part 1. Exoplanets and exomoons. Are there different types of astronomers?
So there are many ways that you might try to split astronomers into different categories. One might be the more technical versus the more philosophical. Another axis we often use is one who is more of a theoretician versus someone who's an observer. I personally don't like these definitions because when one assumes a label and you call yourself, I am a theorist, well, that basically tells yourself, okay, that means I'm going to be scared of going to the telescope and getting my hands dirty. So I kind of prefer to work in both worlds. I work with data and I work with theory. And I think that combination of the two is very powerful. If there was one way to split astronomers though, I would say it would be on a question, a scientific question. And that would be, what is the thing which most drives you? And I think that question really is, do we want to understand whether we are alone in the universe, whether there is other life out there? That is one fundamental question that drives many astronomers. Or do we want to understand how the universe works? Why did the Big Bang happen? The large-scale structure of the universe, the why of how everything operates in the universe. That is a different type of astronomer, and there are cross matches between them, but I think those are the two dividing lines I see amongst my colleagues.
What is an exoplanet?
An exoplanet is short for an extrasolar planet. The extra means outside, solar means the solar system. So it's simply a planet outside the solar system. And whenever you look up at the stars and you see these stars which are many light years away, sometimes thousands of light years away, turns out a lot of those stars have planets, and those planets are what we call exoplanets. Astronomers have been trying to look for planets for a very long time, over a century and a half, in fact. But the first time that we really believed that one of these claims was real was in 1992, a detection of two planets around a pulsar. This is essentially a dead neutron star that has collapsed at the end of its life, a very exotic star, and yet we found two super-Earths around it in 1992 by Alexander Wolfskan and his colleague Dale Frail. However, a lot of people weren't that excited or maybe galvanized by that detection at that time because it was such a strange star. We really wanted to find planets around normal stars, by which we mean stars like the Sun. And so that first happened in 1995 by Michel Mayor and Didier Queloz. That was the star 51 Pegasi b. And actually that detection was awarded a Nobel Prize in the year 2017. So that was really the first time that astronomers realized this is the real deal, and many other astronomers started to jump into the field, and the field of exoplanets as we know it today was really birthed.
Were there previous claims of exoplanets?
I think a remarkable fact in the history of exoplanets is that the first ever claim of an exoplanet was made in 1855 by Captain William S. Jacob in India at the Madras Observatory, so 170 years ago. So we think of exoplanets as a fairly new field, but people have been claiming these things for a very long time. Now, of course, that planet didn't turn out to be real, and if you go forward in time, there's basically a century and a half of astronomers making spurious claims over and over again, thinking there's a planet there, someone coming along and saying, hey, hang on, actually, there's not really a planet there. So this garnered the field a very dirty reputation. Other astronomers would kind of mock and laugh those looking for exoplanets. It was like looking for aliens or even looking for ghosts, things which just seemed like every time the people made the claim, it didn't turn out to be real, and so why should we believe these astronomers? It wasn't really until, I'd say, the early 2000s that this field really blossomed into a legitimate scientific, credible field. And even in 1995, when that first Nobel Prize winning planet was discovered, that was 51 Pegasi b, even then, I remember seeing papers, historically seeing papers, it was a bit before my time, but seeing papers saying, this planet is not real. This could be the sun misbehaving. It could be the star doing something strange. We can't really trust this. And so for a very long time, those who studied exoplanets walking down the corridor would have to endure sneers and mockery from their colleagues because it just really wasn't taken that seriously.
Theoretically, how many exoplanets could exist?
So in the last 20, 25 years, astronomers have been detecting many exoplanets, and we now have just over 5,800 confirmed exoplanets in our catalogue. Now, that sounds like a very impressive large number, but of course it's just the tip of the iceberg when we compare to the number of stars and expected number of planets in the entire galaxy, let alone the entire universe. In our galaxy alone, there's at least 100 billion stars. So if every single one of those stars has planets, which seems to be what we find out there, then that would mean that there's 10 billion people on Earth. Every person on Earth would have 10 stars, 10 planetary systems just to themselves. You could spend your whole life just studying those 10 planetary systems and learn all about the different moons and rings, and it would all be yours. And that's just how much is out there. It is a mind-boggling amount of data for us to study. And that's why it is such a challenge. And we are really just in the very earliest of phases. I think in history, future history, we will look back at this time and say this was the golden era where they really didn't know what to expect. And it was a very exciting time to be an astronomer and uncovering these secrets for the first time.
How do we search for exoplanets?
So astronomers have been trying to look for exoplanets for a very long time, over a century and a half, and we've come up with a large number of different methods and strategies to try and accomplish that goal. If you go back to the earliest claims, that was Captain William S. Jacob in 1855, he was using a method called astrometry, which really means measuring the changing positions of a star on the sky, just seeing whether it wobbles left to right, up and down on the sky. Now, the reason why that might happen is because if there is a planet which is very far away from that star, it will have a large pivot point, essentially, a large axis to wobble that star back and forth, and we can see that in the motion on the sky. So I think the reason why astronomers early on thought this astrometric method would be so successful was because there was an astronomer, a German astronomer called Friedrich Bessel, who had used it to great success to discover binary star systems, Sirius and Procyon, for example, in the early 19th century. So it wasn't surprising that astronomers thought this would be a good method to use, and it also wasn't surprising because you look at the solar system, most of the planets are fairly far away from the sun. However, it's not very good for finding planets which are close to the star. And as it turns out later on in history, that's what we found a lot of. It turns out planets do often get close to the star, and that method just isn't very good for finding those types of planets. So the radial velocity method, which was the method that the Nobel Prize was ultimately awarded to for the discovery of 51 Pegasi b in 2017, but it was a 1995 detection, that used this another wobbling star technique. But instead of looking at the changing position of the star, it looked at the changing speed, the velocity of the star, but only the speed along the line of sight, hence the word radial, along that direction that you see. So as the star comes towards you, it gets blue shifted a bit, and as it comes away from you, it gets red shifted. And we detect those blue shift red shifts, and we can infer there is an orbiting planet around it. When those detections were made, there was some skepticism about whether these blue shift redshifts were really planets orbiting those stars, or perhaps was something strange going on the surface of the star. Maybe there was some kind of bubbling, frothing foam on the surface of the star that was tricking us and creating those blue shifts and red shifts. There was a kind of like Jerry Maguire, show me the money. People wanted to see the transit of the planets in front of the star. Show me the transit. And the transit is an eclipse. That's when the planet just simply passes in front of the star. And that's not going to happen every time. You're going to have only a small fraction of planetary systems which are going to have the right alignment that the planet happens to pass in front of that star and causes a dip in brightness. But about 1 to 10% of planetary systems, you expect to see this. And indeed, after about the 10th exoplanet had been discovered using this wobbling star method, we found our first transiting planet. And transits really became the workhorse of exoplanet detection in the years that followed, especially with NASA's Kepler mission, which single-handedly discovered about 4,000 exoplanets using that one technique. So it really makes up the bulk of our present catalog. Now, in addition to those two main techniques, the transit method, which has detected the majority, radial velocity, which has detected a minority, there's also two other plays in the game. Those are microlensing, that's looking at the gravitational lensing of light from very, very distant star systems and things passing in front of them. And on top of that, there's imaging as well. So we can actually try and take a direct photo of a stellar system and see if we can actually image the planets around it.
What are blueshift and redshift?
When we are using the radial velocity technique, we are essentially measuring blue shifts and red shifts of the star due to the gravitational influence of a planet around it. But what does that really mean? You can think of blue shifts and red shifts a bit like a pitch change. And I'm sure you've probably heard of this down the street. If an ambulance or a cop car goes down the street, the siren seems to increase in pitch as the vehicle is coming towards you and then decrease in pitch as it's going away. And that's because the sound waves get squished in a lateral direction as it's coming towards you and stretched out as it's moving away. The same thing happens with light. As it gets stretched out, it gets redshifted. As it gets squished together, it gets blueshifted. So we can see the spectrum of the star shift bluer and redder, back and forth. And in fact, we can see all these individual spectral lines, like the absorption lines of hydrogen and helium, embedded within that spectrum. And that whole tooth comb kind of moves left to right, left to right. And by measuring that, we can tell very precisely how fast that star is moving.
Why are you interested in exomoons?
I have always been fascinated by space ever since I was a small child. I remember lying out on the grass, looking up at the stars and just being amazed by what else could be out there. And so I ended up studying for my PhD, astronomy, at University College London. And I finished that 14 years ago. So I guess you could say that I've been looking up and studying the stars for 14 plus years at this point. And it really is a passion of mine. I'm so happy every day that I get to do this. Despite all of the joys every day of studying the stars, I think we all have frustrations as astronomers, things that we truly want to discover. And for me, that white whale, if you like, would be looking for exomoons. These would be moons around other planets. That is something I have spent more or less my entire career looking for, and yet it is something that we feel should be out there, and we are so close to, like a glimmer on the horizon. It's almost within reach. The obvious question is, why is that so interesting? Aren't the exoplanets enough for you? Why do you have to make this more complicated by including moons in here? Now, for me, I think there are 4 big reasons why this is such an important scientific question to answer. The first one is that these moons could, of course, be habitable in their own right. So we're obviously very interested in counting up how many Earth-like worlds are out there in the cosmos, potentially inhabited worlds nearby. And of course, the moons could be a significant component of that. So we really need to find those habitable moons if we're interested in looking for life out there. Second, a moon can actually help a planet become more habitable. And of course, the moon is kind of an example of this, or at least speculatively. So we have a very large moon. It's the largest moon by mass ratio of any of the planets in the solar system. And it's so large that it actually stabilizes the axial tilt of our planet. It's about 23 degrees and it's pretty locked in there because of the presence of our large moon. Take the moon away and Jupiter's influence would cause the axial tilt to wander over millions of years, and you can show that in computer simulations of the solar system. So that would be very bad. Then we'd have the North Pole pointing at the sun for several months of the year. It would cause chaos to our climate. It might mean it's okay to have simple life, but I would be skeptical you could have an agrarian civilization such as our own on a planet like that. You'd be looking at something more like the three-body problem or Game of Thrones, with these extreme long winters. It might not be the safest place to try and build a civilization. The third reason why I think this is so important is to understand our formation. Are we unique? Are we special? Are we just a run-of-the-mill planetary system? Again, our own moon is a good example here. We think our own moon formed through a giant impact of a Mars-sized body at the beginning of the solar system 4.5 billion years ago that smashed into the primordial Earth, and the collision led to this coalescence of what became the moon. Now, it's unclear, is that a common situation or is that a very special case? It seems to be the only example of such a thing in the solar system, but we really don't know looking out whether that is normal or not. So that's one big reason to try and look for these things. And then finally, Eventually, we will want to be able to take photos of exoplanets. That's something we are moving towards in our field. And when we make those photos, we are going to have incredible resolution. We're going to be able to see this little dot of light, the pale blue dot of light. But really, it's not just going to be a pale blue dot. It's going to be a pale blue gray dot, because we will not be able to resolve the moon and the Earth from each other in those images, at least with nothing that we're planning right now. It'd be very, very difficult to be able to resolve those 2 objects from each other. And that's a big problem, because when we look at that blob of light, one of the things we are trying to do is to look for what we call chemical disequilibria. So that is, you see chemistry embedded within that spectrum of light that you're pulling out that is in disequilibria, and thus tells you that perhaps there is life on that world. Now, of course, the moon and the Earth are obviously in chemical disequilibrium with each other because they're physically separated. A more extreme example might be Titan. Titan has a methane-rich atmosphere, and you can imagine detecting an Earth that does not have life on it, but perhaps has oxygen still, because the water can photolyze through ultraviolet radiation from the sun. So you have oxygen on the Earth, you have methane on a Titan-like moon, and all blends together into a single blob of light. And you would naively interpret that to be a chemical disequilibrium and the smoking gun of life. So if we do not tread carefully, and think carefully about whether there are moons around those planets, we could make the mistake of thinking there is life on these imaged worlds when really there isn't.
What are the challenges to finding exomoons?
Looking for exoplanets is hard enough. Looking for exomoons is just taking it, dialed to number 11. It gets way, way harder. And the reason why is, of course, when we look at our own solar system, the moons are very small. The largest moon in the solar system is Ganymede, and it's only about 40% the size of the Earth. Now, it turns out when we look for these transits, which is the most successful method that we have of looking for exoplanets, you can try and use that same method to look for exomoons, but of course it's going to be more difficult because the thing is much smaller. And in fact, the difficulty scales not just as the radius of the planet, how big it is, but really the radius squared, because that's the area that it blocks out as it goes in front of the star. So if I make something 0.4 the size, like Ganymede is compared to the Earth, it's going to be 2.5 times harder for us to detect those objects. And even the Earth is very, very difficult for our current telescopes to detect. So just purely their sheer small size makes them very difficult to detect. On top of that, they're not in the same place. They're constantly moving around. The planet comes around like clockwork and more or less repeats once every orbital year around the star, but the moon does not. The moon's moving left to right, and that makes it extra difficult for us because we don't even know necessarily where to look for these things. It is a very challenging detection, but I think that's, for me, what makes it so appealing. I've never really been personally interested in doing the industrial easy work, just detecting thousands of things because we can. I've always been personally drawn towards those challenges of doing something new, doing something that seems maybe pushing to the very limits of what it's capable of.
Is there evidence for exomoons?
So we do have some hints of exomoons in our data. And actually in my team, the Cool Worlds Lab, we have claimed 2 exomoon candidates, but they are both kind of strange. And I think it's natural to be skeptical about whether they're really there or not. And that's indeed something we share as well. And the big reason why there is skepticism about these objects is because they're freakishly large. In both cases, we have a Jupiter-sized planet. In fact, it's probably even a bit larger than Jupiter, a bit more massive than Jupiter. And both of them seem to have a moon around them, but that moon is 2.5 times the size of the Earth, or even in one case, 4 times the size of the Earth. So these are Neptune-sized moons, or in between the size of Neptune and the Earth. Very, very large moons, and nobody has predicted that. If you look in the textbooks, you look at all the previous literature, what people expect for moon formation, you will not find a single page which predicts you will find a Neptune-sized moon out there. Doesn't mean it's not real. Nobody predicted the first exoplanets either. Those were hot Jupiters, planets which were bizarrely close to their star and really surprised everybody. And indeed, many people were very skeptical about the reality of those planets for good reasons, for decades that followed. And so it's not surprising that the community is skeptical about the nature of whether these moons are real or not, these supermoons. Personally, I'm giving it better than 50-50 odds, but I really want to see more data before we can have that confirmed stamp of approval on them. The first of these supermoons that was claimed in the literature, Kepler 1625b-I, that's Kepler 1625 is the name of the star, B is the planet, and -I is this moon candidate. That object was actually detected using the Hubble Space Telescope. We looked at the star very carefully. We took a photo every 5 minutes and monitored how bright the star was. And as you look at the brightness of that star, you see one giant dip as the planet passes in front of the star. It's a Jupiter-sized planet, so of course it's a big dip in light. But then you see a second dip in light caused by this moon-like object passing in front as well. This is what got us really excited. The idea that there could be a Neptune-sized moon around this planet. It turns out we could even weigh how heavy that moon should be based off the perturbations of the shape of the planetary transit. And that also came out to be about a Neptune mass. So we have a Neptune mass moon, a Neptune radius moon, and it's in an orbit which looks fairly comparable to what the moon has around the Earth, in fact. So all of those things give me some assurance that this thing could be real, but of course we want to go back and get more observations, maybe with the James Webb Space Telescope, to really prove whether this is real or not.
Could exomoons be inhabited?
There are several advantages that an exomoon could have as a potential habitable home for humanity or another species out there in the galaxy. One is that the majority of stars in our galaxy are so-called M-dwarf stars. These are stars which are much smaller than the sun, and therefore, in order for a planet to be close enough to have liquid water, it has to be pretty close. So close that it ends up getting what we call tidally locked to the star. So the planet will always have one side facing the star at all times. Of course, the moon is tidally locked to us, so we're kind of familiar with this idea of tidal locking. The downside of that is, of course, that's going to play havoc to the climate of these exoplanets. So therefore, the vast majority of known habitable zone Earth-like planets have this huge problem that they may not be habitable at all because they're all tidally locked. However, the moons will not suffer this problem. Yes, they will be tidally locked, most likely, to the planet, but they will not be tidally locked to the star. And so it turns out that both sides of the moons will receive equal amounts of illumination. There's this idea that Pink Floyd said there's the dark side of the moon. That's not true. There's a far side of the moon. Both sides of the moon get equal amounts of illumination, and so too it is for these exomoons. And so in that sense, they can escape this big pitfall of habitability that I think many, many exoplanets will suffer from. On top of that, one of the criteria that we often imagine being necessary for habitability is having a strong magnetic field around the planet. Now, that's true for planets. Moons are often so small they couldn't generate their own magnetic field, but they don't have to. They could actually hide and borrow the magnetic field of their giant planet they're around. So they have several advantages like this, and I think we could imagine either humanity spreading out between the stars or other civilizations doing so, choosing these moons as opportune places to build a colony simply because there's so many of them and they get around many of these dangers that planets can often have.
How could new telescopes affect our search for exoplanets?
So for me, I think the long aspirational dream of exoplanets is, of course, maybe to one day visit them, but probably in my lifetime, maybe more realistically, is to take a photo of them, to really see what their surfaces, their clouds, their atmospheres truly look like. And including, of course, looking for satellites and rings around those planets as well. At the moment, we simply can't really do this. When we look at these distant stars, they're often so far away that if there are planets around them, it is very, very difficult to resolve those planets spatially. It all just gets blended into this one blob of light, starlight. However, we are building technologies like the chronograph and the starshade, which can block out that starlight. Combined with increased resolution, we can actually pull out pale blue dots or pale orange dots or green dots, whatever the colors of those planets are, and see the entire solar system as like a family portrait for the first time. Now, probably still, even with the aspirational dreams of what's going to happen in my lifetime, I doubt we'll have the ability to take an image as we see it of the Earth. We're not going to have a high resolution 4K image of the Earth from space for an exoplanet. We'll probably just have a single pixel image of a planet, even so. But as that planet rotates around, it will present different sides of itself to us. And so we can actually use that rotation to reconstruct computationally a possible image representation of those planets, which is faithful to the data that we see. So I think we will have some very coarse images emerging from this. Especially if there's a moon, actually. If there's a moon that passes in front of the planet, that will actually act like a rasterization scan and give us even more detailed spatial information about the surface of those planets. That is what I'm really excited about. I think we all want to see these things with our own eyes. Just calling back to that famous image in 1991 that the Voyager 1 spacecraft took of the Earth, taken from about the distance of Neptune around the sun. The Voyager 1 spacecraft looked back and took this wonderful photo called the pale blue dot. And I think in my lifetime, I would love to see a pale blue dot of an exoplanet for the first time. So there is a plan in the late 2030s, early 2040s by NASA to build a telescope which can do this. It is currently being called the Habitable Worlds Observatory, or HWO, and it will be roughly a 6-meter class telescope that will go into space and try and accomplish this. So still a bit of a wait, but hopefully all in our lifetimes.
Why do human beings want to colonize other planets?
I think it's an interesting question to ask. Why do we actually want to look for these worlds? Why do we want to maybe even one day visit them and colonize these exoplanets in the far future? For me, I think what we're doing right now is a bit like being the map makers. If you go back 400, 500 years, we really didn't know what the shape of the globe was or where the continents were, and people were voyaging out into the unknown and drawing the first maps of what might be out there. And I think a lot of what we're doing right now is kind of similar as astronomers. We are map makers, essentially. We are looking out and trying to draw not the continents, but the maps of the exoplanets that our distant descendants might one day visit and perhaps even build colonies on. And the question is, why do we have this urge? I think it's something fundamental to us as human beings. Ever since we left Africa, we've had this compulsion to explore, to go over the next hill, over the next mountain, cross that river and see what might lie beyond. There is the promise of a better life, more resources, building a more advanced civilization. That call for exploration is somehow just built into our spirit, I think, to want to do this. Ultimately, there is a practical reason for doing it as well, which is, of course, having all of our eggs in one basket here on the Earth is a fairly risky strategy. It would only take one giant asteroid to strike the Earth and knock us all out of existence. Or, of course, it could be a gamma ray burst or a supernova. The universe has no shortage of ways of exterminating life on the Earth. And so if we can put our presence on other worlds, it perhaps gives us a better chance of survival. However, one thing we have to be very cautious with this idea of expanding human presence is, of course, there could be living creatures or even living beings, civilizations out there on these worlds already. And we really don't have any more right than they do to put our presence out there onto these worlds, especially if there's someone already there. So there is interesting ethical questions about how we should actually conduct ourselves in such an exploration phase.
What are some ways we could inhabit an exoplanet?
If we want to explore beyond our solar system and visit even the nearest exoplanet to us, which is Proxima Centauri b, 4.2 light years away, it would take even our fastest spacecraft many thousands of years to cross that distance using chemical propulsion technologies, which is what we have relied on so far. These distances are so great compared to our human technologies that there's no way a human lifetime could ever last long enough to survive the journey and expect to step foot on the other side on these planets. So how do we solve this problem of one day visiting these other worlds? Is there a way that we could get over chemical propulsion and reduce that journey from thousands of years to maybe decades or even years? Now, unfortunately, we can't really think of a way of doing that with a human being on board, but we can think of ways of doing that with very small spacecraft, even micro spacecraft. So there's ideas to use solar sailing or even really light laser sailing to push a spacecraft not only to nearby planets in the solar system, but beyond to exoplanets many light years away. The idea here is to have a very, very light spacecraft. Think of an aluminum sheet that is just maybe even 20, 100 atoms thick, a very, very thin sheet of material. And yet it is huge, maybe many meters across. And you shine a gigawatt laser at that large sheet of aluminum, it will be propelled by light pressure to very high velocity. Now, of course, the payload is going to be very small. We're talking about like a microgram, payload on board this thing. That's going to be something like a very small chipsat, essentially, on board. It's not going to be able to do a lot, but it could probably take a photo. It could probably have an AI ChatGPT loaded on board that could maybe interact with people on the other side. But the idea of putting a human being on board one of those things is completely impossible. Just the mass of a human is far too heavy for these vehicles to work in that way. So I think the most realistic proposal I'm aware of getting a human being to actually physically step foot on another exoplanet within sort of 100 years timescale would probably be, you don't actually have a human being on board the spacecraft. Instead, you just have embryos, frozen embryos that perhaps are even genetically engineered to be well suited for the destination planet they're arriving at. Now, of course, there has to be something on board that's going to unpack those embryos and grow them into human beings. And so you can imagine having a robot on board that would accomplish that goal. In fact, this idea was recently explored in Ridley Scott's Raised by Wolves series. And I think it is most realistically the best way I can imagine of seeing a human being on another exoplanet in, let's say, the next century. It's difficult to imagine exactly what an astronaut arriving on an exoplanet is really going to expect, because after all, with our current technology, we only have very limited information about what these exoplanets are truly like. We know their mass, their size, we know their chemical composition, but we don't truly know much more beyond that. So what are the things they might encounter? One of the problems might be there might not even be a solid surface on these worlds. There are these types of planets which are in between the size of the Earth and Neptune. We sometimes call them super-Earths, we sometimes call them mini-Neptunes, but really we don't know. They could have a non-solid surface, which would obviously be a challenge for astronauts to build a colony in the way that we would normally recognize. On top of that, we don't even know really what the conditions would be like for an astronaut in terms of the gravity or the terrain. The gravity could be much stronger than that of the Earth. Of course, on the Earth we have 1g of gravity, and if you go into an airplane and you're a fighter pilot, you experience maybe 2, 3, 4 g's of pressure on your body, and that's fine for a few seconds, but to live that way would be extremely stressful for the human body. I can't really imagine a human being coping with 4 g's of gravity for a prolonged period of time. On an exomoon, there'd be other challenges, of course. You would have this beautiful giant planet potentially in your sky, many times larger than what we see the moon in our own sky. It would mean at nighttime there really wasn't a nighttime. You'd still have essentially a kind of afternoon level of light even during the middle of the night because of all the reflected light coming off your giant exoplanet around you. And that would raise some interesting questions about potentially what the biosphere itself would be like. Would animals have developed to live differently to nocturnal creatures on our own planet? It could be a very hazardous place to be an astronaut if we're not very careful. But this is the human spirit, to go to a new place, explore, and I'm sure, the people who are willing to do that will be very aware that they're taking a huge risk and are probably accepting of that risk because that's something built into us, at least some of us, to want to go to those places and take the risk anyway.
What are some cultural ramifications of expanding civilization?
One of the interesting cultural questions about a civilization which spreads out between the stars is that space is very, very big. In fact, if you spread out far enough, you could end up on one side of the galaxy to the other, which is 100,000 light years across. So that would mean that simple messaging, limited by the speed of light, would take 100,000 years. It's very difficult to imagine how a culture could remain monolithic over such a long distance, that in fact these cultures would splinter off and perhaps even forget their origins, as is often explored in the sci-fi books and the movies Dune, where civilizations really aren't sure where the original planet even is anymore. So I think a question we often have when we think about the looking for aliens is that we kind of assume there'll be a monolith. We'll assume they'll all act the same way, but truly, even if they spread out from a singular source, the sheer distance scale will ultimately force them to fracture into a diverse range of civilizations and cultures. And that's interesting when we think about looking out, that we're not going to encounter just maybe one single galactic federation, but really a menagerie of different beings.
Do you believe humans will actually inhabit another planet?
Personally, I think the idea of humans expanding and colonizing other planets is feasible in our own solar system, but it is a stretch to imagine really happening for exoplanets, just because of the sheer distance to them. The sheer challenge of traveling that long in space with a human body is going to be very difficult to imagine overcoming. I'll never say never, but just it's not my bet that that would be a likely thing to happen. But I do think I can imagine a human presence across the solar system in the far future, and having an extended human presence in the form of AI agents, robots, and machines, children, if you like, spreading out to those more distant outposts and sending us back information and being our ambassadors to the greater part of the galaxy.
Part 2. The case against the rare Earth hypothesis. What is the rare Earth hypothesis?
The rare Earth hypothesis was popularized in a book by Ward and Brownlee in 2000, and it really just suggests that maybe the Earth is very, very special in terms of a long list of criteria. So, for example, maybe there are exoplanets out there which have the same size and mass as the Earth, but they have a different chemistry. Maybe they don't have the same kind of ocean salinity as we do. Maybe they lack a large moon. Maybe they lack plate tectonics or a magnetic field, and it goes on with this long list of possible things which might be necessary for life. And on each one of those criteria, you can make a good case as to why life on Earth indeed requires those conditions. However, we really don't know whether life elsewhere does or does not require the same conditions that we enjoy here on the Earth. And I think that's one of the reasons why there is definitely not a wide acceptance of the rare Earth hypothesis.
What do we call exoplanets that resemble Earth?
There's a few different terms that we throw around when we talk about Earth analogs, and Earth analogs is one of them. You could also say Earth twins, Earth 2.0, Earth-like exoplanets, and there really isn't a good consensus about what we mean by specifically each of those terms. We could have a planet which has the same mass and radius of the Earth, and to all accounts it looks like the Earth, but remember Venus has basically the same radius and mass as the Earth, and that is clearly, when you zoom in on it, a very non-Earth-like exoplanet. So as astronomers, we're kind of stuck with this problem that when we see these planets which naively resemble the Earth, and we could legitimately write a headline that said Earth-like planet found, we don't truly ever know, and we won't ever really know until really a person sets foot on that world and reports back on the weather conditions on that exoplanet. So we are stuck in a predicament as astronomers as to what to call these things. I'm personally okay with calling them Earth-like, with the proviso that there's always some extra thing we could discover that could discount that. Science has this strength of being able to revise itself. It doesn't have a dogma. So just because we called something Earth-like in the past doesn't mean it has to be Earth-like indifferent to whatever discoveries we make in the future. Science will update itself depending on new information.
What are the most common types of exoplanets?
Humans love to analogize, and astronomers too, and so we often take the planets in the solar system and even the sun as a kind of benchmark for how we compare different objects that we see. So we often talk about sun-like stars or solar analogs, and nobody really gets too upset if you use those terms, but the moment you say Earth-like, you could start rustling some feathers. On top of Earth-like and sun-like, we also have, of course, the other planets in the solar system. We have a Mars-like exoplanet, would be something that was about half the size of the Earth and about a tenth of the mass, and we've actually found a few examples of those in the exoplanet catalog. The most common type of planet we have found is a Neptune-like exoplanet. These are things which, as the name says, have the same mass and radius as Neptune, but we don't truly know in the same way whether an Earth-like planet is truly Earth-like, just how close to Neptune these objects truly are. Perhaps the most mysterious type of planet that we have found are planets which are in between the size of the Earth and Neptune. So that's a size of 1 Earth radius up to 4 Earth radius, and we are finding things which are 2, 3 Earth radii in between those two limits. And we don't have anything like that in the solar system. Perhaps Planet 9, a hypothesized planet on the outskirts of the solar system, might be such a planet, but as far as the planets that we are familiar with, we don't have such a thing. And so that has left us in the dark about the true nature of those objects. There's nothing to analogize to. Are they scaled up versions of the Earth with a rocky surface, or are they scaled down versions of Neptune that are just kind of mini gas giants? We just don't know. They perhaps could be something completely different, like a giant ocean world, in fact, something that we simply don't have in the solar system at all. So this is where our analogies kind of run into the end of the road, but I think it is useful, at least when we talk about prioritization. If we're going to build a mission that's going to try and look for life, it certainly makes sense that you would focus on maybe the Earth-like planets, with the understanding that, of course, they might not truly be Earth-like when you look a bit deeper.
Have we found any Earth-like exoplanets?
There's a long history of people claiming planets which look Earth-like, Earth 2.0, Earth twins. Some of them have evaporated and have now gone away. I think a famous example was Gliese 581G. That got a lot of people very excited, but of course within I think 2 or 3 weeks, another independent team showed that this planet was not real. And so I think the public has been exposed to many headlines in newspapers and on TV that have claimed Earth twin found, and haven't really kept track with the fact that many of those Earth-like planets didn't stand the test of later scrutiny. And so there is a sense of exhaustion at this point. I think a lot of people probably naively assume that we have a whole bunch of Earth twins at this point, and that's really not the case. Of course, a lot of this really depends on what we really mean by an Earth-like exoplanet. For me, I would have 4 criteria. It would have to be roughly the same mass as the Earth, the same size of the Earth, have a similar temperature to the Earth, and be around a sun-like star. Now, we know of many exoplanets which tick those first 3 boxes, but to tick all 4 is very tricky, and in fact we have 0 exoplanets which tick all of those boxes. Probably the closest planet to it is called Kepler 452b. Unfortunately, soon after it was announced, people contested whether that planet was real or not. So it's sort of in that in-between grey territory where it's not been refuted, but it's not exactly confirmed either. That is probably the closest Earth-like planet I can think of in the catalogue. On top of that, though, we have many exoplanets that tick the other three boxes. They are Earth mass, Earth size, and have the right temperature, but they're not around a sun-like star. They're around, most typically, these red dwarf, M-dwarf stars, as astronomers call them. These are planets that are much closer into the star. TRAPPIST-1 is a great example of an exoplanetary system that has multiple planets in the habitable zone of its star, which are all rocky. However, we just don't really know whether these red dwarf stars are sufficient for life to begin around them. Maybe there is something about the radiation that comes off those stars that is so different that it prevents the emergence of life, or perhaps exterminates it after a period of time. So if we want something where we're absolutely assured this satisfies all the criteria that the Earth enjoys, unfortunately we still lack a true Earth twin.
How common could Earth-like planets be?
The primary way that astronomers are trying to count up the occurrence rate, how often are Earth-like planets out there, is using data from a mission called the Kepler mission, launched in 2009 by NASA. Now, this mission lasted for about 4.5 years, and it tried to look for the transit signals of planets, including potentially Earth-like planets, around 200,000 stars. However, in its long search for about 4.5 years, it found 0 true Earth-like exoplanets. It found many planets around smaller stars and bigger stars, but nothing around the sun which looks just like the Earth. So that left us in a pickle. How do we tell what the occurrence rate of Earth-like planets is if we have 0 detections? Now, of course, that doesn't mean there are 0 out there, because Kepler only looked at 200,000 stars, and it's not a perfect telescope. There could very well be many Earth-like planets out there which the data was just too noisy for us to pull the signal out of. And so astronomers have to do a correction. We have to kind of guess how many Earth-like planets did we miss. The way we normally do this is to look at the trends that we see in larger planets and planets which are closer to the star. So you can count up how many Jupiters do you see, how many Neptunes do you see, how many sub-Neptunes do you see, how many super-Earths do you see, and you kind of draw a line through that trend and you extrapolate what you think is happening at the Earth-like level. However, when you do extrapolations, the different mathematical formulations you come up with for that extrapolation will lead to different results. And so this is why we see a great diversity of answers in the literature about what this E to Earth, the occurrence rate of Earth-like planets, truly is. And in fact, estimates range all the way from 1 plus or minus 1% of sun-like stars have Earth-like planets, all the way up to over 100%. These are all published papers in the literature by respectable colleagues who have been very careful with the data. And I think the short answer is we just really don't know. As wonderful as Kepler was, it didn't quite succeed in its original goal of trying to find those Earth-like planets. Unfortunately, if it had just lasted maybe 6 or 7 years rather than 4.5 years, I think it would have got there. Unfortunately, it lost 2 reaction wheels on board the spacecraft, which cut off the mission short. And so we're probably going to need another mission to really answer this question in finality. So NASA has had this policy for a long time of follow the water. That's where we should look for life. We should look at the places where liquid water is possible. And that really defines what we mean as astronomers when we talk about the liquid water zone, or really the habitable zone. That's what it means. It is the distance from the star at which you could imagine liquid water being stable on the surface of a planet. And this policy kind of makes sense because all life on Earth requires liquid water in order to survive. But perhaps that is just a property of Earth-like life, and maybe there is life out there which does not require liquid water in order to survive. If so, we should perhaps extend the range at which we look for different types of life to being maybe Jupiter-like exoplanets, Venus-like exoplanets, Mars-like exoplanets, even Titan-like moons. We can imagine a very broad range of things we could look at. But practically, that raises a problem. As human beings, as astronomers, we only have finite resources. Only so much money is, in the end of the day, given to astronomy. We have to prioritize where we look. So when people hear that astronomers are following the water and focusing on the search for liquid water, I think it's understandable that could be maybe frustrating. Like, oh, astronomers are so short-sighted, they don't even consider the idea of other planets potentially having life as well. That's not the case. We are certainly willing to entertain those ideas and consider them quite seriously. The real problem is we just can't look at everything. We have to choose, and it's a very difficult choice to make, but it seems to make sense that at least for the first detections of life that we're going for, focus on a place where we know it actually succeeded, which is somewhere like the Earth.
What makes a planet habitable?
So there's a whole bunch of possible criteria we can imagine as being necessary for life, but of course it is all a bit speculative because we only have a single data point, which is life on the Earth. Nevertheless, these ideas range from things like plate tectonics, for example. Plate tectonics is thought to be important because it allows plates to get subducted under one another. That material gets pulled back down into the magma where it can eventually come out back again through volcanism. This is a way of recycling carbon. It forms the carbon cycle, which without, I think it'd be difficult to imagine how we'd have the same kind of biosphere we enjoy today. Another example would be a magnetic field. The Earth enjoys a fairly strong magnetic field that gives us the aurora borealis and the northern lights, these beautiful spectacles that we get to enjoy. But there's also a real benefit for life, and that's it protects the surface from extreme radiation. Now, we could imagine still, I think, life surviving beneath the surface or in the oceans without that magnetic field. But if we want to have an agrarian civilization such as our own, I don't think you'd be able to have agriculture in the absence of that protective field. Another example might be a large moon. Our own moon stabilizes the axial tilt of the Earth. The Earth has an axial tilt of about 23 degrees, and it's kind of locked in place by the presence of our unusually large moon. If you took the moon away, Jupiter's gravitational influence would cause it to wander over millions of years, playing havoc to our climate. So that would also be potentially bad for a civilization such as our own. And then finally, you might imagine extra criteria such as the landmass fraction or the salinity of the oceans or the chemical composition of the planet itself. And we can go on and on adding extra criteria, and they're all reasonable, but they're all kind of unproven because at the end of the day, we only have us to look at this point.
How do asteroids play into the rare Earth hypothesis?
An interesting factor to consider in the rare Earth hypothesis is asteroid strikes. How often does the Earth get struck by a large asteroid? Obviously, this has happened in the past. The dinosaurs were knocked off famously about 65 million years ago with the KT transition impact. But it seems like life consistently recovers from those types of impact over a period of millions of years if the frequency between those impacts was much shorter, maybe just 1 million years between such impacts, maybe it'd be impossible for life to recover to the same kind of level that we have on the Earth today. So the real question is about the frequency of those impacts. And when we look out into space, of course, Jupiter seems to have a big influence in that. Jupiter has often been cast as a sort of double-edged sword. Maybe it's a good thing that we have a Jupiter because it kind of hoovers up all the asteroids with its giant gravitational potential and thus protects the Earth. It could be the Earth's shield, essentially, in the solar system. But others have argued that it does the opposite effect. And in fact, it is a great attractor, and it pulls material in towards the inner solar system from the outer solar system, and some of that slingshots around Jupiter and actually comes straight at us and ends up causing a giant impact. So there's still an active debate about whether having Jupiter is a positive or a negative. And similarly, there's an active debate about whether asteroid strikes are a positive or a benefit on the Earth. If we had no asteroid strikes whatsoever, maybe the dinosaurs would have kind of continued and that would have been where we are today. No intelligent life ever would have emerged on the Earth. Perhaps you need some frequency of evolutionary resets to give life a chance to get going again and explore a different path. Astronomers are trying to be creative, though, about what we consider to be the range of habitability. So, for example, there are planets which orbit around these M-dwarf stars which are so close to the star they probably become tidally locked. Now, that would seem very bad to have one side of your planet always facing the star, probably not good for the climate, but when we've done climate simulations of those planets, which took a bit of creativity to engineer the models to work in such a case, you find that you actually form like a cloud sombrero on the side of the planet which is facing the star. And that cloud sombrero cools down that one side of the planet and allows the whole planet to remain habitable. You can also push it even closer in and get very desiccated worlds similar to what you see in the Dune movie series and the book series, where you have these giant sand deserts and yet still there's just enough water to imagine life clinging on to survival as well. On the other side, we can imagine a planet which is very far away from the star, normally outside of the habitable zone, too cold, but astronomers have played with ideas of adding in a huge hydrogen envelope around the planet, which acts as a very effective greenhouse gas. This is like CO2 but on steroids. It gives us this huge greenhouse effect which allows the planet to remain warm even far away from the star. So we are certainly thinking about ways in which we could push the envelope, quite literally, of where life could be. However, I still think the majority of us think it probably makes sense to focus on that inner habitable zone, but consider the fringes as possible areas as well.
What is your anti-rare Earth argument?
One of the primary tools that astronomers use to think about the abundance of life in the universe is the famous Drake equation, first written down by Frank Drake. It is essentially the number of stars in the galaxy multiplied by a long list of possible factors, such as how often do you have planets, how often are those planets Earth-like, how often does life begin on those planets, and so on and so on. Now, when we look at this, it's like a narrowing filter, and you can imagine with the rare Earth hypothesis adding on extra terms, such as having how often does the planet have a large moon? How often does it have the same mass as the Earth? How often does it have the same land mass fraction the Earth has, or the same ocean salinity or chemistry, etc., etc.? And you can imagine adding on hundreds, even thousands of extra parameters onto the Drake equation, which get ever narrower. And of course, if you multiply a very large number of fractions together, you'll eventually get zero. And I think this is one of my big problems with the rare Earth hypothesis, is that it's a very narrow view of how life began and how life must survive on other planets. All of these factors have to be true. It is a singular path. And that is a path which has indeed led to success, but perhaps there are different paths parallel to us, which are completely different, yet also lead to life. And so the Drake equation simply multiplies fractions by each other, but perhaps truly what it is missing is an additive sign. There is a second path below it, a different way of getting to intelligent civilization, and a different way after that, and a different way after that. And so perhaps not only should we be multiplying all those things, but also adding up all those parallel tracks. And it is that addition that we just really can't do without a lot of creativity and discovery, because right now we only have this sole example to look at.
Part 3. The search for alien life. Why is the search for alien life so popular?
Many astronomers are really driven by the search for Earth twins because I think deep down the natural endpoint of this whole goal of looking for planets is to answer the question, are we alone? That is a burning itch that I think many of us have our entire lives wanted to answer. I'm sure many of you feel the same way as well. So I think that was what really drives us. But you know, whenever you have a temptation, a goal, an aspiration that you're reaching for, it is so easy to get blindsided and drawn into dark avenues that aren't really true, especially in science. That can happen quite often. And so we've already had several claims of not only Earth-like planets, but even life. There's been claims of life on Venus, there's been claims of life on interstellar asteroids, and of course there's many UFOs that we often hear about. So there is a natural temptation to look at anything that seems anomalous, that seems a little bit different, and immediately reach for aliens. Because of course, deep down, I think a lot of us really want that to be the answer, that we are not alone. It's kind of a terrifying thought that we truly could be alone. This drives us, it inspires us, but it's always a risk that we could go too far into that temptation and see aliens where there's none really there, and we have fallen prey to that trap many times in the past.
What is life?
What is life though? What are astronomers actually ultimately hoping to detect? Defining life is an incredibly difficult task, and there is definitely no consensus about how to call such a thing. Maybe it's actually better to call it more like porn, like you will know it when you see it, rather than having a strict textbook definition of it. NASA have certainly tried to have a definition. For a long time we had a definition from NASA that said it is a self-replicating chemical system capable of Darwinian evolution. And that's pretty good, but maybe chemistry isn't actually necessary. Maybe you could have an AI system or self-replicating technology that would still resemble life in many ways, but wouldn't actually involve the kind of chemical systems that we're familiar with. So whenever you come up with one of these definitions, it's really easy to poke holes in it and say, well, what about this? What about this? And I think it's just too hard for us to come up with a singular thing to say this is exclusively what life is until we've discovered more examples of it. That's the quest that we're on. We're going to look out, we're going to try and find examples of things which resemble properties of what life does, and then we'll do the hard work of truly trying to classify what actually is life in the first place and where do we draw our boundaries.
What are the requirements for life?
The necessary conditions for life on a planet are still up for debate as well. We really don't know exactly where the limits of life are. When we look at life on Earth, there are some organisms, especially extremophiles, that can cope with fairly large ranges of conditions. So for example, there's some thermophiles that can range from minus 25 degrees Celsius, and then you have other extremophiles which can live at 125 degrees Celsius. So 150 degrees Celsius range of diversity. But the fact that extremophiles today can survive in such an extreme range of temperatures doesn't mean that life could begin under such an extreme range of temperatures. Maybe the nascent conditions for the birth pangs of life to begin with, the abiogenesis event, the spark of life which created all life on the Earth, maybe that requires very special and subtle temperature range that cannot be violated. And perhaps things as cold as minus 25 degrees Celsius are just way outside of that range. These are questions we just don't know. What were the initial conditions on the Earth that led to the emergence of life? Similarly, we can't assume that just because extremophiles on Earth can only survive from minus 25 to plus 125, that means that life elsewhere could not survive under even more extreme conditions, because it could be based, of course, on different chemistry and use different thermodynamic rules than the ones that our life currently uses. So there's a lot we don't know. But I think the idea of just narrowing in on the places where liquid water could survive, which is from 0 to 100 degrees Celsius, that certainly makes a lot of sense, because even those extremophiles still require liquid water at some part in their life cycle in order to survive. So I would be comfortable with that as an initial hunting ground, with the idea that we might perhaps extend that to more diverse environments as we go on.
What is the Copernican principle?
The Copernican principle, named after Nicholas Copernicus, also goes by the name of the mediocrity principle, and sometimes in cosmology is an extension of it called the cosmological principle. And all of these ideas essentially say the same thing, and that's that where we are, where we live, even when we live, is typical. Everything about us is normal, and therefore we should expect that if we go to another part of the universe, it will look basically the same as it does here. And usually, this is a pretty good argument. Take, for example, the instance of Neptune. We have a Neptune, in fact, really two Neptunes in our solar system, Uranus and Neptune, and they don't seem to really play any part in our own evolution out there in the distant part of the solar system. And so you might reason if we have two of them, perhaps other solar systems should have them too, by this mediocrity principle, the idea that we are typical and normal. And indeed, that would be strikingly true. When you look out at these exoplanets, that's what we find. We find Neptunes all over the place. They're indeed a very common type of planet. But here's where it runs into problems. Let's imagine we use the Copernican principle to argue that the Earth has an oxygen-rich atmosphere. Therefore, all of the planets in the solar system should have an oxygen-rich atmosphere or liquid water, whatever you want to choose. And of course, many features of the Earth are incredibly unique and special to the Earth itself and are not found on any of the solar system planets, and perhaps not found elsewhere in the universe too. We just don't know. And there's a good reason for that, and it's called the weak anthropic principle. And the weak anthropic principle basically points out that you can only live in a place where conditions are suitable for you to live. So it's not surprising that we don't live on Pluto. It's not surprising that we don't live on a moon of Neptune, because those places are so cold, they have very little atmosphere, that of course a human being could never have evolved on such a world. We would of course live on only the subset of exoplanets, or planets in general, where the conditions were right for life. And those conditions themselves could be very, very rare. Maybe there is only 3 Earth-like planets in the entire universe, as far as we know. It should not be surprising that we find ourselves living on one of those 3 Earth-like exoplanets, because perhaps that is the only place where we could live, and all the other places are just simply devoid of life. So when we use the Copernican principle, my big caveat would be, look, it's okay to use it when it has nothing to do with our survival, our emergence. Neptune, fine. Neptune has nothing to do with why we're here. There's no way which Neptune affects life on this planet. But the moment you use it in a case which is connected to our existence, which is predicated upon our existence, such as maybe the presence of a large moon or oceans on our planet, then we have to be very careful. I don't think in those cases we can reliably use the Copernican principle, because if we do in the solar system, it clearly fails. So in that case, I think we should just take a beat and really analyze how connected we are to the statements that we are making. And that's why I do not buy the argument that by the Copernican principle, life must be common. It is kind of a circular statement, I would claim, to make that argument.
What is the Kardashev scale?
One way that we have attempted to classify hypothetical alien civilizations is with the so-called Kardashev scale. So the Kardashev scale basically splits civilizations up by energy usage. And maybe that's a somewhat archaic way of thinking about it. Today, I think maybe we might think about capabilities more than energy usage, but this has still remained a very persistent way in which astronomers think about how we might split up civilizations. So a Kardashev type 1 civilization is defined as a civilization which uses all of the energy which is incident upon its planet, and we are not there yet. We do not have our planet covered in solar panels and use that amount of energy. That still greatly exceeds our current global energy consumption. A type 2 civilization would be one which not only uses all the energy on the planet, but uses all the energy of the star. So you might imagine a type 1 civilization being able to control their weather and their climate, but a type 2 would be able to control the entire solar system. They're able to move planets and moons around at will as they needed. And practically speaking, in order to harvest all the energy of a star, you'd probably need to build some kind of giant shell around that star, often called a Dyson sphere, after Freeman Dyson, who first proposed that idea. And that shell, or swarm of material, would absorb all of that starlight, which you could use for whatever you want to do, computation, manufacturing, whatever advanced purposes these civilizations might have for such an energy need. And if you just go another step further, you can do it to Kardashev type 3, and that's one that not only controls their solar system and all of the energy output of their solar system, but now goes to the entire galaxy. I think most realistically, you might imagine a civilization like that living around Sagittarius A star. That's the supermassive black hole that lives right in the center of our galaxy, and that thing spews out gigantic amounts of energy that you might imagine a very advanced civilization harvesting and using. And indeed, I think it's an interesting place that we should consider looking for alien civilizations. Maybe not an intuitive place, but a place that I think we have a good argument as to why they might end up in the center of a galaxy.
What is Hart's Fact A?
Hart's Fact A, named after Michael Hart, is connected to the Fermi paradox, the idea as to how come we don't see aliens out there if it seems like they should be out there. And Fact A in particular points out that there are no aliens on Earth right now. We don't see a civilization cohabiting the Earth with us. We haven't been totally colonized by an alien civilization. It appears to be a very lonely planet with just one civilization, which is us, living on it right now. What I like about Fact A is it's kind of indisputable. It's one of the hardest points we can really say in astronomy. I can't claim that a distant exoplanet doesn't have an extraterrestrial civilization on it, but I can be much more assured about the fact that we are not currently cohabiting the Earth with another alien civilization. I feel much more confident making that claim. And even that claim, as weak as that might seem, does put some interesting limits upon the behavior of other civilizations. It means, really, that a galactic civilization does not exist, that there is no instances of a marauding berserker type civilization that just decided to gobble up every exoplanet, every real estate it could find, and turn it into another colony for itself. Because if that had happened, the whole Milky Way would have been colonized by now and we wouldn't be here. This really connects to the ideas of self-replicating probes, also called von Neumann probes, which have been argued for a long time to be a real problem for those thinking about life in the universe, and especially life in the galaxy. For it turns out that even though the galaxy is very large, 100,000 light years across, even traveling the galaxy at sort of Voyager 1, Voyager 2 type speeds, the speeds of our current spacecraft, it should have been eminently possible to have colonized the entire galaxy many times over during its 13 billion year history. That's a long period of time for all of that colonization to have taken place, and you really don't need to have fast rockets to have colonized the entire galaxy by now. Yet clearly, that hasn't happened, as Fact A demonstrates. And so that's interesting. It means that maybe civilizations do emerge elsewhere in the galaxy, but they never have the will or the capabilities to conduct such an expansion phase, such an aggressive expansion phase where they take over the entire galaxy, because of course we wouldn't be here had that had happened. That is probably one of the strongest data points I think we have.
Are there any recent developments in the search for life?
We don't have any evidence for life outside of the solar system. And so when we talk about the propensity of planets to form life, probably the only strong data point we have is the fact that we're here, but also more importantly, when life appears to have emerged on the Earth. And strikingly, it appears to have emerged very, very quickly in the Earth's history. Now, this naively could be taken to say, well, therefore, if life starts quickly, it must be an easy process. But we have to be careful when making such claims. Perhaps the evolutionary process to go from the simplest forms of life to something like us, a self-aware entity which can do all of this paleontology, all the statistics and math, maybe that timescale takes 4 billion years pretty much all the time on these types of planets. And if it consistently takes 4 billion years for that process to plays out, life kind of has to get going pretty quickly, else there wouldn't be enough time for us to have emerged in the first place. I think a surprising fact about the Earth people don't realize is that it will likely become uninhabitable to complex life in less than 1 billion years' time. And so life really does have to get going quickly, else there just wouldn't be enough time in that evolutionary process to get to us. So we could naively look at that early start to life and say, therefore life is easy. We add this complexity of evolution, say, maybe not so quickly. But eventually, if we push that early start to life further and further back, you eventually overwhelm even that evolutionary timescale, and you do end up with a genuine result that actually there's no way around it. Life actually is an easy process, despite all of the nuance of that evolutionary argument. And indeed, I think for the first time, we are seeing signs that we are crossing that threshold. There was a recent result that we are able to date the emergence of life on the Earth to 4.2 billion years ago. And for context, the oceans formed 4.4 billion years ago. So within 200 million years, really a cosmic snapshot, we had the conditions ready for life emerging, and we went all the way from there to the first organisms on our planet within 200 million years. That is such a short period of time that it overwhelms that evolutionary argument, and you have, for the first time, I would claim, strong evidence, not definitive evidence, but strong evidence that life is indeed an easy process to get going, at least under the conditions that the Earth enjoyed.
How long might it take for intelligent life to develop?
So based off the early start to life on the Earth, we might genuinely think that simple microbial life could be quite common, at least assuming that Earth-like conditions are common in the universe. So we'd have lots of planets out there with simple life on it. Now the interesting question then is, how often do those simple life forms develop and evolve all the way up to something that is like us? Here it took 4 billion years, perhaps it takes a little bit less or a little bit longer on other planets. And so we might look forward to the future and say, if it takes 4 billion years for this process to happen, surely as the universe ages, there should be an emergence of more and more civilizations into the future. But we actually have to be a little bit careful with that argument too, because stars and planets have finite lifetimes. They don't last forever. They eventually die. Our own Earth will die as a habitable biosphere in less than 1 billion years due to the evolution of our star. As the star evolves, it grows in luminosity and will actually eventually make the Earth too warm for liquid water and thus life on our planet. So there will be a collapse point in less than 1 billion years when that happens. So this sets a time constraint for life in the universe. Not only do you have to have life get going fairly quickly, but then you also have to have enough time for that evolutionary process to play out and get to something like us. And this immediately rules out a large swath of stars as possible places where a civilization might live. For example, stars which are more massive than the sun have shorter lifetimes. They burn through their nuclear fuel much faster, and so perhaps those stars wouldn't have enough time for a civilization to develop on them. Vice versa, we have the M-dwarf stars, stars which can last for trillions of years in some cases. And so potentially that might be the place that in the far future we can imagine civilizations emerging, and we would be the first, the weirdos of the universe who lived around a sun-like star early in its history, and civilizations emerge much later on around these M-dwarf stars.
How do we look for life on other planets?
There are two basic strategies which we might attempt to search for life in the universe. One is with a so-called biosignature, that is a signature of biochemistry essentially on another planet, and a second is a technosignature, the signature of technology. Now technology obviously requires that not only do you have life, that an advanced civilization also developed on those planets. And so that naturally seems like a smaller piece of the pie to look at. However, those technosignatures could be very, very loud, heard from millions of light years away potentially, and could also perhaps be very persistent. We can imagine a civilization maybe building a beacon or something that could last for billions of years to perpetuate its knowledge into the cosmos. So a simple balance is not so easy in weighing which of these options would be most fruitful. The biosignature case certainly has had, I'd say, greater attention from entities like NASA and government funding agencies, because after all, you don't require all this evolutionary complexity. You can just have simple life and potentially still be able to see them. The way biosignatures work is to look for gases that are emitted into the atmosphere, which are uniquely produced by life. At least that's the theory. The problem is, it's very difficult to find gases which are indeed uniquely produced by life. Lots of gases can be produced through geological processes as a side product, and so that can become a false positive to our search efforts. A classic example of this is oxygen. Of course, plant-based life manufactures oxygen on the Earth through the process of photosynthesis, and so it would seem like oxygen would be a good thing to look for, especially because oxygen is a very reactive molecule that really doesn't want to hang around in an atmosphere. Something has to be making it, because otherwise it just reacts with stuff and oxidizes and so quickly disappears. The fact that our planet has a sustained level of oxygen proves essentially that life is here. At least that's true on the Earth. But we could imagine different types of planets where oxygen is being manufactured without the need for life at all. One possible way this could happen is through a process called photolysis. So ultraviolet radiation from the sun strikes the upper atmosphere. And if there is water in that atmosphere, H2O, the H2O will be split up into the hydrogen and the oxygen separately. Now, hydrogen is very, very light. It's the lightest element you can have, and so it's very easy for it to escape into space and simply be lost, like letting go of a helium balloon that disappears into the sky. But the oxygen is heavier and it sinks, and so you can end up with just ultraviolet radiation plus water in the atmosphere generating a significant amount of oxygen in a planet without any life involved. And so that signature would be a false positive for us. If we're not careful, we would interpret that to be life, whereas in fact, it is not. And so astronomers, chemists, biologists, we're involved in this game now of trying to imagine all of the different signatures that life could produce and all of the different confounding factors that might trick us, and trying to find those unique combinations that we really trust as being the smoking gun that this has to be life. So it's a very complex chemical field that we're involved in, but ultimately a tractable question, but a question that we still need to work really hard on.
Why should we be cautious in our search for life?
From a scientific perspective, the question we really care about is looking for life on these exoplanets, and indeed planets in the solar system as well. So for example, Mars is a good case study. We have sent robots there which have attempted to look for life, and a big question has always been, are we accidentally carrying life with us to that planet? And thus, when we do the experiment to look for life, are we maybe accidentally detecting just life which hitchhiked a ride and joined us on that journey and arrived at Mars without really that being the intention? It's actually very, very difficult to totally sterilize a spacecraft and eradicate every single spore on the surface of that thing. There is essentially always going to be a little passenger which hitches a ride with you. But we of course want to minimize that as much as possible to reduce the chance of that being a false positive. And so this raises some interesting ideas about where is the best place to look for life, because Mars has had a lot of contamination, not only from spacecraft from the Earth, but also asteroids. Even before we had a space program, there was still material being constantly swapped between the Earth and Mars just by meteorites being knocked off one and landing on the other. So perhaps life has long contaminated Mars even before humans were around. But there are places in the solar system where that shouldn't have happened. If you look at the icy moons of Europa and Enceladus, for example, those are protected by a thick ice shell, many kilometers thick, which should really prevent any material being able to penetrate through that ice and get into that subsurface ocean. So for me, I think those are the most interesting places to look. We could drill down through, hopefully be very careful about contamination, and we would have a pristine location where if we detected life there, I think we could be pretty assured that was not a contamination from the Earth. This was a genuine second abiogenesis event. And once you have two starts to life in the solar system, that would essentially establish that life really would be everywhere in the universe. Will
we ever answer the question of whether we are alone?
I think we have to accept the possibility that even though we're on this quest to look for life in the universe, we may never get a conclusive answer either way. I certainly hope that we can find an answer, but it is possible we never will. For the truth is that space is just a very, very huge expanse to try and explore and have conclusive answers on. One of the hardest scientific aspects of this is that you can't prove a negative. So I can never prove to you that Mars does not have life on it. I can look at the surface and claim on the surface I am 99% sure there are no microbes. But then you could also say, well, what about underneath the surface? Have you checked there? What about underneath that rock over there? Or behind that canyon or behind that hill? And so I can never totally prove, even on the nearest planet to us, Mars, that it does not have life on it. So what hope is there in that sense of ever proving that we are alone? It's impossible to prove we are alone. We will always wonder about that. We can get a series of null results, of negative results, but it's never going to establish true loneliness. The fact that space is simply so large means this is a challenge that maybe we should be patient. I mean, I hope we can get an answer in my lifetime. I would love to know the answer in my lifetime. But this may be a journey that humanity undertakes over not just centuries, but maybe millennia into the future, in a similar way that Galileo 400 years ago was first starting astronomy and couldn't have imagined how astronomy and the discovery of exoplanets and cosmology would be born from his creation of the telescope. We have a long journey ahead of us in astronomy too to answering this question about life in the universe. But it is the great question, and a question which I think many of our future descendants will be inspired to continue studying.
How does our experience on Earth inform our concept of life?
When we're looking for aliens, of course, the question is the Fermi paradox. Then Enrico Fermi asked this question, look, if there's so many good arguments as to why life should be out there, how come we don't see any evidence for them? And the Fermi paradox has puzzled us for a long time, and it has a huge number of possible solutions. And the solutions which we come up with to explain it are often a reflection of what's happening in our own civilization right now. So an emerging one is thinking about AI and the computer age that we're living through, that maybe as we become more and more sophisticated, we might get bored of this real world and we might instead choose to live in some kind of virtual reality environment, upload our brains, interact with AI agents, enhance our intelligence, and almost get fed up of the idea of even living in this messy, dirty, gross real world and confine ourselves to this clean intellectual environment that's detached from physical space. And if we are thinking that way, and some people are thinking that way, maybe advanced civilizations also eventually go that way too. Of course, that's speculative. We don't know if they're going to engage in such an activity, but I think it's interesting to look at these ideas as mostly a reflection of our own concerns and worries. If you go back to the 1960s, the most common explanation for the Fermi paradox was nuclear annihilation, because that was the concern that the world had at the time. Because of the Cuban Missile Crisis and the Cold War, people were very worried that a nuclear annihilation event could happen, and that would be a natural explanation for the Fermi paradox. So if we're thinking about some kind of computerization phase as an explanation for the Fermi paradox, it is perhaps mostly a reflection of where we are in our own society, and maybe in 50 years we'll look back at it and kind of laugh and think it was silly.
Part 4, the dark forest hypothesis. What is the SETI paradox?
SETI, S-E-T-I, is the search for extraterrestrial intelligence. It is essentially an effort to try to detect the radio signals, or possibly even more broad than that, laser signals, whatever signals you might want to look for, from another civilization out there in the galaxy. Now, there is a strange aspect of SETI. We have this kind of paradox that we are listening for radio signals from beyond, from these other planets, but we don't really transmit much, I mean, very, very little. So we are kind of assuming that there will be a civilization out there, a benevolent civilization that is interested in spending huge amounts of energy and electricity powering their giant radio transmitter, saying, hey, we're here, look out for us. And yet we have no systematic program of doing that. We've sent out one or two little messages, but we certainly are investing billions of dollars shouting out into the cosmos saying, hey, we're here, come say hi.
Why are we reluctant to send messages out into space?
SETI, S-E-T-I, has always had an interesting relationship with the idea of transmission, of communication. In fact, when the field first began, it was actually called SETI, and that C stood for communication. And very quickly, they changed their minds and realized that the idea of a two-way communication was maybe a bit ambitious, and it might be better just to focus on searching for the signal rather than truly trying to have a dialogue. So on the other side, we have the idea of METI, messaging extraterrestrial intelligence, also called active SETI. So this is where we actually send out a message hoping to get a reply at some point in the distant future. Of course, that could be hundreds or even thousands of years, given the vast expanse of space beyond us. So this is a very common concern. Stephen Hawking had the concern that, maybe we should be very careful about communicating to the civilizations, because whenever you've had a more advanced civilization engage with a less advanced civilization on the Earth, that has usually ended very badly for the less advanced one. And so if you extend this out to the galaxy, maybe we should be careful about sending out our presence into deep space. And certainly this is a trope that has been played with in science fiction as well. If you look at Liu Cixin's book, The Three-Body Problem, that's where we get the idea of the dark forest hypothesis, the idea that civilizations could be out there, dangerous, marauding ones who want to take over and colonize your planet, and so it's much better to just be quiet. Don't let anybody know that you're here. I do have a bit of an issue with this idea of resistance to METI and resistance to communication, and that's that we, humanity, are already engaged in the activity of trying to build telescopes and future facilities that can detect life whether they want to be detected or not. So you don't have to send out a radio wave for me to be able to detect your civilization. We could potentially detect their satellite systems, their Starlinks. We could detect their solar panels on their surface. We could detect their industrial space presence, even the chemical pollutants in their atmosphere from industrial processes. There are so many ways that we could imagine being able to tell there was a planet that had a civilization on it, an advanced civilization on it, without the need for a radio message, that it's a little bit archaic to assume that that's the only way that a civilization would be able to know of another one's presence. I suspect if there is another advanced civilization out there in the galaxy, they already know that we are here. Maybe not the presence of Earth's current level of technology, because simply the finite travel time of light is going to limit us to about 200-year radius, essentially 200 light-year radius, where another civilization would know that we're doing industry. But certainly beyond that, in the broader galaxy, they would know we had an oxygen-rich atmosphere, they would know we had photosynthesis, they would know that the Earth was inhabited by creatures. And so I think it would be difficult to argue that we should be very, very quiet, because otherwise they will never know we're here. I suspect they are well aware that this planet is inhabited with or without our radio signals. So when we talk about the dark forest theory or resistance to METI, I think an interesting way to look at this is what's called a risk quadrant, often used in financial analysis or insurance companies as a way of evaluating the pros and cons of any activity, any behavior that you engage in. So in our case, we have two possible activities we could do. One would be to transmit, and the other one would be to stay quiet, to hide ourselves. And then on the other axis, we would have the two possible outcomes. One would be that they're friendly, and the other one would be that they're hostile. Now, if we transmit and they are friendly, then there's going to be some net benefit. Let's call that a +1 benefit. If we transmit and they are hostile, that's going to be a very bad situation for us. That could be a -infinity, some very large number, a bad direction that would take our civilization, because it could be an extinction level event ultimately. On the hide axis, we have two possibilities. They're friendly and they're hostile, but it really doesn't make any difference because the outcome is 0-0 in both cases. So when you average out these two rows in this risk quadrant, the activity of transmitting, you have +1 added onto negative a very large number, which is going to be another very large negative number. And then on the bottom axis, you have the hiding. Well, hiding is just 0 + 0, so it can lead to another 0. So there's no net gain or benefit of doing that activity. And when you compare those two on this risk quadrant in this game theory type approach, you would end up concluding that it makes no sense to transmit. Because if you transmit, there is, yes, a possibility of some gain, but there's also a very real possibility of a huge loss, which is your very existence. And so on that axis, a lot of people would claim it's just not worth it. There's no reason why we should even take that gamble. But of course, the way you might be critical of this naive analysis is that yeah, maybe they actually already know we're here anyway. This whole idea of transmitting is maybe an archaic way of thinking about how they would look for other civilizations. They don't need to listen to our radio signals. They can just take their giant telescopes and take a beautiful image of the Earth and see our satellite systems and know that there's an advanced civilization here, regardless of whether we are trying to transmit or not. So I understand the common argument as to why we should be careful, thinking about almost the sociology, the game theory approach of thinking about their behaviors. But it's a little bit more nuanced than that when you really think about the capabilities of one of these advanced civilizations.
What is the three-body problem?
Planets orbit around stars, and if there was only one planet and one star, the math would in fact be incredibly simple, and you could predict precisely the position, the velocity of that planet at any moment in time, either in the future or in the past, given a set of initial conditions. If you have a second planet in the system, so now you have three bodies altogether, unfortunately the math gets much harder, and even very, very slight perturbations in the initial conditions lead to wildly different results for the final outcomes of these systems. This is known as chaos theory, and in particular in application here to three bodies, hence sometimes called the three-body problem. And of course, this is not just for three bodies, but if you have 4 or 5 or 6, this thing gets even worse. An example of this is in the solar system. If you look at the future of the solar system and predict the positions of the planets, it turns out that in about 1 billion years' time, about 1% of the simulations that we generate, Mercury gets ejected from the solar system altogether, and Venus and Earth swap places. This happens in about 1% of these chaos theory simulations. So this just goes to show you how difficult it is to predict the future. Even in the solar system, where we know the positions of the planets very, very well, the three-body problem makes these predictions inherently very difficult to make.
What are the challenges to sending messages across such large distances?
Communicating over large distances, and really we mean extremely large distances when we're talking about the galaxy, requires a lot of energy. And so this is a real problem. If you want to communicate your presence across the entire galaxy, you're going to need a transmitter which is ultimately the size of a planet or even the size of a star, and it has to be turned on all the time. For as soon as you turn that signal off, of course, the light wave will stop, and so you're going to have a finite time in which you could be detected. So an interesting question is, how could we build a communication system that would be much more long-lived? There's an interesting idea by Luke Arnold who suggested that rather than trying to build a giant transmitter, be it radio or laser or whatever it is, instead you do something passive. And so his idea was to exploit the transit method of looking for exoplanets. We could build a thin, giant structure in space of a very elaborate shape that would transit in front of the star, maybe a giant triangle, for instance. And as this triangle transits in front of the star, it would create a very remarkable and alien-looking transit signature, something which nature should never produce, that we would be able to tell from afar there must be a civilization who built that. And the beauty of this is that it requires no power system. The sun itself is powering that for billions of years. It requires no mechanical parts, no maintenance. It's just going to sit there for billions of years saying, hey, there is somebody around this. And I really love the idea of going a step further and trying to build more elaborate shapes that could even encode information within those transit signatures. You can imagine the Galactic Encyclopedia being embedded within elaborate floral patterns, almost embedded within these shapes transiting in front of stars.
What are the linguistic challenges to communication?
I think there's 2 parts to communicating with alien civilization. The first part is simply making a loud signal, that they can see that somebody is there. It doesn't necessarily have any information embedded within it, it's just a loud hello. But the second part, and more interesting part, is how do you actually communicate some kind of story of who you were or what you know, or some request or ask that of the civilization. That requires language. Now, of course, they're not going to, unlike Star Trek, they're not going to have the same language that we have. They're not all going to be aliens speaking English or have universal translators that we can easily make sense of. So it has been a real problem to think about what we might encode within these messages. And certainly there have been early attempts to do this. The Arecibo message sent in 1974 was an attempt at trying to build a universal message that anyone can understand, and it really worked within the language of mathematics. The idea being that an advanced civilization would surely have to have discovered mathematics if it was to get to a certain level of sophistication, and so that is the language that we could attempt to communicate with. Another example that was made in the early 1970s was the Pioneer plaque. This was a replica right here of a physical plaque that was put on board the Pioneer 10 and 11 spacecraft that was an attempt at communicating to an alien civilization. Perhaps it will never be found, but it was an effort to do so that communicates really using pictorial messages and a little bit of math. For example, on this side of the plaque, we've got a representation as to where the solar system is relative to 14 nearby pulsars. These are like clocks in the universe. Each of these lines represents the distance from those pulsars, and the binary code that is stitched along there represents the frequency of those pulsars. Actually, another interesting bit is that in the future, the pulsars' location and their timing, their frequency, will slightly drift. And so an alien civilization who discovered this plaque could not only figure out where the solar system is, but the year in which this plaque was launched, because this will change slightly over time. So this simple message, even though it's pretty small, already tells a civilization, hey, this is where we are, this is the third planet from the sun that we came from, this is what we look like on this planet, and this is the vehicle that we use to get to you. It even has a little depiction of the hyperfine transition of hydrogen, letting them know that we understand quantum mechanics as well. So a certain level of sophistication was required to make this plaque. And these are the kind of efforts that we're engaged in, is thinking about what universal things would they know? Surely they would know quantum mechanics. Surely they would know maybe general relativity. Surely they would know advanced mathematics. And it's those that we have to use as a common basis of language. Otherwise, we might be stuck in a situation like in the film Arrival, where we require some linguist to come in and think really hard about how to translate these patterns, which are maybe non-mathematical, but might have some cultural connection to those civilizations as well.
What's the most likely way we might communicate with other life in the future?
So I'm a big proponent of technologies for communication that are passive, if you like, that don't require an active power system. If we try to build a communication program that requires federal funding and energy and maintenance, it's inevitably going to fail after 10, 20 years or whatever, when someone decides that's too expensive to do. We need something which can last for not only hundreds of years, but potentially billions of years. For we have to accept that even if we are pessimistic about the odds of cohabiting the galaxy with another civilization right now, into the far, far future, tens, even hundreds of billions of years into the future, there could very well be a large number of civilizations which emerge and explore the galaxy and eventually come and arrive at the solar system and wonder who might have lived here in the past. And so for me, one of the most interesting ideas for communication is to leave something physical behind for them to find. And of course, this is an idea that was played with the film 2001: A Space Odyssey, where there's these monoliths which are left within the solar system, especially beneath the lunar surface. And I think that is a really terrific place to leave something. The moon has no active geology, it has no atmosphere, it has no weathering. So anything that you leave on the lunar surface is going to be preserved for a very, very long time, millions of years. Think about Neil Armstrong's footprints. They're going to be there for at least 1 million years. And if you build something physical, a large structure on the surface, that's going to be even more robust. And the extra benefit would be, of course, to bury it maybe a meter beneath the surface, where you're now protected from micrometeorites as well. This would be probably the safest place in the solar system, in my opinion, to leave something that we could potentially encode a message, maybe an LLM, an AI agent that can communicate, teach another civilization about who we were, our mathematics, our accomplishments. And I think to some people this idea can be a little bit depressing. We maybe have the idea that we want to actually meet them on the White House lawn, shake their hand like we see in sci-fi films, and have a communication, a dialogue in real time. But if we're being more realistic about it, maybe that's just never going to happen. And if we concede that that might be an improbable circumstance, perhaps the next best thing we can hope for is to communicate not in a simultaneous sense, but through time. We could leave something behind in the same way that our ancestors speak to us through the monuments they left, be it the pyramids or the Stonehenge, these structures which are left behind and speak to us from the past. We too have an opportunity to build something on the moon, I would claim, that could last for billions of years and be a record. And perhaps the most likely advanced civilization that is going to discover that relic that we leave behind will be a future descendant of the Earth. For the Earth has another 1 billion years left to go in its evolutionary history of chemical biology still taking place. And think about all the advanced evolution that has occurred in just 500 million years. We've gone from single-celled organisms to us in 500 million years on this planet. What's going to happen in another billion years? We will probably disappear at some point. And I can imagine not just one, but perhaps multiple advanced civilizations re-arising on this planet, having their own space ages. And they will go to the moon, find this relic, and perhaps know something about who we were. To me, that is the most likely alien encounter we're going to have.
Want to support the channel? Join the Big Think members community where you get access to videos early, ad-free.